coming from a beloved country that we hope to reach with the hypersonic flight in the next future, in a short time, the Japan. We have Mr. Ueno that will address the problem Aerothermodynamic design of JAXA hypersonic passenger aircraft, ICARI project. Mr. Ueno, 15 minutes for you. Thank you. The floor is yours.
Yes, thank you very much. Today, I'd like to introduce the research activity at JAXA on hypersonic transport. In this presentation, I will focus on aerothermodynamic design. And the Hikari project, Europe-Japan collaboration is briefly introduced. This figure shows JAXA's R&D roadmap on hypersonic transport. We have developed a hypersonic turbojet engine named PCTJ, pre-cooled turbojet engine. Owing to pre-cooler, this engine can be operated at up to Mach 5. And we are now currently developing small-sized PCTJ. The length of the engine is about 2 meters. And using this small engine, we are planning flight test at Mach 5. And after that, we are aiming at hypersonic business jet using medium-sized PCTJ. And finally, we are aiming at large-sized aircraft, large-sized passenger aircraft. I will introduce this large-sized aircraft. The number of passengers is 100. Flight Mach number is 5 at an altitude of 25 kilometers. We are aiming at trans-Pacific flight from Tokyo to Los Angeles. It will take about 2 hours. And baseline configuration of our large-sized aircraft was defined by using multidisciplinary design optimization. The aircraft shape and engine size were optimized considering the mission requirements such as range performance and flight time. And optimized length is about 90 meters. The weight is about 400 metric tons. We have 2 fuel tanks at the front and rear part of the fuselage in order to control the position of center of gravity. And the cabin is placed at the center fuselage. And for this baseline configuration, detailed aerothermodynamic design was conducted. In the MDO, aerodynamic heating was not taken into account, and the TPS weight was estimated using empirical relation. Here, CFD analysis and wind tunnel test were conducted to evaluate aerodynamic heating. In the wind tunnel test, it is difficult to realize flight condition because Reynolds number is so large. So at first, CFD was validated by wind tunnel test. And after that, based on CFD result at flight condition, the TPS was designed. And the method of CFD analysis is shown here. JAXA's UPAX code was used. And the wall condition is isothermal wall. And at wind tunnel condition, the wall temperature was set at around 300 Kelvin, considering the wall temperature of wind tunnel model. And at the flight condition, the wall temperature was set at around 800 Kelvin, considering the usable temperature of TPS material. Ueno tunnel test was conducted at JAXA's hypersonic Ueno tunnel. The free stream Mach number is 5, and diameter of the test section is 0.5 meter, and the maximum duration is 120 seconds. We have 2 wind tunnel models. this smaller model is a full configuration model having a fuselage, wing, and vertical tail. The Reynolds number is less than transition Reynolds number, and boundary layer is laminar. But at flight condition, the boundary layer becomes turbulent. So we have to measure the aerodynamic heating for turbulent boundary layer. So to increase the Reynolds number, in this large model, the length is enlarged, and P0, the stagnation pressure is increased from 1.0 to 1.5 megapascal. As a result, the Reynolds number becomes higher than a transition Reynolds number. In addition, in this model, the boundary layer trip was attached around the nose. And in this test, the temperature was measured by infrared thermography, and assuming a semi-infinite one-dimensional heat equation, the aerodynamic heating was evaluated. This figure shows the result of wind tunnel test for smaller model. The boundary layer is laminar. And left figure shows the aerodynamic heating on the upper surface of the model. Here we can see high aerodynamic heating. This is due to the vortex. The flow is separated separated at the side edge of the fuselage, and vortex is generated on the upper surface of the model. And this vortex sinks the boundary layer thickness. So the aerodynamic heating is increased in the region where this vortex is attached. This figure shows a comparison between CFD analysis and the wind tunnel test. They show a qualitative agreement. However, in the wind tunnel test, the aerodynamic heating is slightly overestimated around nose and around wing leading edge. This is due to the thickness of the wind tunnel model. When the thickness of the wind tunnel model is small, it becomes difficult to distinguish between heating on upper surface and heating on lower surface. So this assumption, the semi-infinite one-dimensional heat equation, is not correct. So the aerodynamic heating is slightly overestimated in the region where the wind tunnel thickness is small. But CFD and wind tunnel test shows a qualitative agreement. This figure shows the result for larger wind tunnel model. Here is the boundary layer trip, and around here we can see the effect of vortex, also in the turbulent boundary layer. And CFD and the wind tunnel test again shows a qualitative agreement. To compare it more precisely, the two-dimensional plot is shown here. This figure shows the aerodynamic heating along x-axis, along center line of the fuselage, and along this line. And in the region of boundary layer trip, the boundary layer is laminar, and aerodynamic heating is lower than that of CFD analysis. But behind the turbulent behind the boundary layer trip, boundary layer becomes turbulent, and aerodynamic heating shows a good agreement with that of CFD analysis. However, along this line, CFD shows slightly larger aerodynamic heating. We think this is due to the vortex. From this figure, the vortex seems to be diffused more widely compared to that of CFD. And this difference in the diffusion of vortex may affect the aerodynamic heating. And from this figure, the aerodynamic heating is larger in CFD analysis. So the TPS was designed TPS was designed based on the CFD result. And this is the result at CFD. This is the result at flight condition. And the TPS was designed using one-dimensional analysis. The method is not shown here. I will introduce the result of the. I will introduce only the result. And in TPS design, the material of TPS was selected, and thickness of TPS was determined. And around the nose and around leading edge of the wing, the aerodynamic heating is around 100 Kelvin per square meter. In these regions, the super alloy, the Inconel honeycomb, should be applied. But other than these regions, the aerodynamic heating is around 20 kilowatt per square meter. In these regions, the titanium multi-wall can be applied. So summary, the result of wind tunnel test and CFD agreed qualitatively. And CFD showed larger aerodynamic heating. So different turbulent models should be tested in the future. And TPS was designed based on aerodynamic heating obtained by CFD, and the TPS material was selected. And finally, I will introduce the Hikari project. On Japanese side, industry association, the engine company, university, and JAXA joined this collaboration. We have several objectives. Among them, in JAXA, we are in charge of propulsion design. Our task is to evaluate the performance of hypersonic pre-cooled turbojet engine. And status is shown here. Last year, the Mach 4 direct connect test was conducted. And this year, Mach 4 window tunnel test was successfully conducted. And obtained engine performance will be provided to European company, European partner in August. So summary, we are planning for experimental vehicle with small PCTJ flying at Mach 5. The budget is not secured yet, but we are trying to perform the flight test in the future. Thank you very much.
Thank you, Mr. Ueno, for